guys, and welcome to episode 2 of our Trig Substitution series. Now, I would recommend watching the introduction first because in the introduction we kind of outline how we're drawing these right triangles and how we're assigning what sides go to which. On here you will notice that I do have the rules written over here, and that's going to help us figure out which triangle to use. And then over here I have the basic integration rules, which we will use those as well. So in this video, we are going to go through an example. And in this example, the best method of solving it is to use trig substitution. So without further ado, let's go ahead and work through this example. So we're going to find the integral of dx over x squared times the square root of 9 minus x squared. The first thing that I like to do is look at the basic integration rules. And if I find one that fits this, I'll use it. If I don't find one that fits it exactly, then I'm going to need to try this trig substitution. And how I know that I have to do trig substitution, because that's a big question. How do I know to do that? Is because it looks like we have a Pythagorean theorem type thing right here. So let's go ahead and look down our rules. And it looks like 18, 19, or 20. Well, we don't have 18 exactly. We don't have 19 exactly. And it almost looks like we have 20, but we actually don't have 20 exactly. Because remember, u would be the x component of it. And this is saying u squared minus a squared. Well, we have a squared minus u squared. So none of those are actually going to work. And so we need to try something else. And we're going to try trig substitution. It's okay if at first you don't recognize that these are supposed to be trig substitutions. That will come with time. This is going to be trig substitution because we see that square root of 9 minus x squared. And that 9 minus x squared is going to be like a squared minus u squared, where a is 3 and u is x. So let's go ahead and draw a triangle. And then we need to figure out where these things are going to go. Now, you want to look at this component of it first. And that component is definitely an a squared minus a u squared, where a is 3 and u is x. So we want to look over on these, and which of them have an a squared minus a u squared? Oh, number 1. Number 2 is a squared plus u squared, and number 3 is u squared minus a squared. So we are going to set up our triangle like number 1. So for integrals involving the square root of a squared minus u squared, we're going to let u be a sine of theta. Now in this case, our u is really x. So we're going to say x is a sine of theta. And a is 3. So let's go ahead and fill out this triangle using what we know from here. So what we know is that a is 3. So let's go ahead and write a 3 right here. We know that u is x. So let's go ahead and put an x right here. And we know that the square root of a squared minus u squared is 9 minus x squared. Using this triangle and using what we know here, we have a lot of information here that we can use for substitutions. We have a lot of information that we can use for substitutions, which is pretty cool. Now, using our right triangle trig, we know that sine of theta is x over 3. I want you to see where this is coming from. So sine of theta is x over 3, which means that if I wanted to get x alone, I would multiply by 3. Now, how did I know sine of theta was x over 3? Well, opposite over hypotenuse. So x equals 3 sine of theta. That gives us something to substitute in for all of our x's up above. Now, this gives us more information here that the square root of a squared minus u squared is going to be cosine of theta. a cosine of theta. And so this right here is actually going to be replaced with 3 cosine of theta. Knowing this right here, you don't actually have to draw the triangle, but I think drawing the triangle makes it a little bit easier to see. So instead of using these rules, I'm going to show you how to do this all by hand now, and then we'll relate it back to this. So I have a method for replacing my x's. I need a method for replacing my dx. And so let's go ahead and take the derivative of this. The derivative of x is going to be 3 cosine of theta d theta. Now I have a method to replace everything in here. So let's replace all of our x's with 3 sine of theta. Let's replace all of our x's with 3 sine of theta. And let's replace all of our dx's with 3 cosine of theta d theta. So now we're able to replace everything, and I'm going to try to be really good about keeping my colors. So pink is going to get replaced with 3 cosine of theta d theta. Green is going to get replaced with 3 sine of theta, and then remember that this is squared because of the squared there. We're not replacing the squared. We're only replacing the x. Now this is going to be the square root of 9 minus 3 sine of theta squared. The rest of this is now a matter of simplifying. And what you're going to see is you're going to see where this a cosine of theta comes into place. And in the future, you'll no longer need to write this out. You will just know that this is going to be replaced with a cosine of theta. But let's go ahead and simplify this so that you can see where this is coming from. So right now, what we're going to have is 3 cosine of theta d theta. This is going to multiply into 9 sine squared of theta. This right here is going to be the square root of 9 minus 9 sine squared of theta. That, the top's going to stay the same. This is going to stay the same. Now here, I'm going to factor out a 9. I'm going to factor out a 9, so I'm going to have 9 here. That's going to leave me with 1 minus sine squared of theta. Sine squared of theta is a Pythagorean identity. That's a Pythagorean identity. And the Pythagorean identity states that 1 minus sine squared of theta is really the same thing as cosine squared of theta. And so this is going to be 3 cosine of theta d theta, 9 sine squared of theta. It's the square root of 9 cosine squared of theta, which we can actually take the square root of. We can actually take the square root of that. So this is going to be 3 cosine of theta d theta over 9 sine squared of theta times, well, the square root of 9 is 3, the square root of cosine squared is cosine of theta. Okay, now we got to simplify. I notice that I have a 3 cosine of theta in my numerator and in my denominator. Let's cross those things out. So what I'm left with when I cross those out is d theta over 9 sine squared of theta. I'm going to look on this list. Can I integrate that yet? I don't see a 1 over sine squared of theta here. But I do see a cosecant squared of theta. And 1 over sine, one of your reciprocal identities, 1 over sine is cosecant. Meaning I can rewrite this as 1/9 cosecant squared of theta. And now I can integrate this. Now I can integrate this because I have this rule right here. The integral of cosecant of theta is negative cotangent. So this becomes negative 1/9 cotangent of theta plus c. Now, it would be so cool if we were done. That would be so nice if we were done. But we have this in terms of theta. And we started our problem in terms of x. This is in terms of theta. We started in terms of x. We need to end in terms of x. But we do have a method to do that. This is cotangent of theta. I could go back to my original triangle and I could figure out what is cotangent of theta. So I'm going to scroll back up to our original triangle. Remember, cotangent, I don't know why that made it a circle. This says cotangent. Cotangent of theta is adjacent over opposite. Adjacent is the square root of 9 minus x squared, and opposite is x. So I could replace cotangent of theta with this. I can replace cotangent of theta with that. And when I replace cotangent of theta with that, this is what my final answer becomes. Negative 1/9, the square root of 9 minus x squared over x plus c. That is my final answer using trig substitution. So that's my final answer using trig substitution. Let's do a quick recap here as to what just happened. That was a lot of information. We started our problem with this. We looked at our basic integration rules and nothing seemed to fit. But we recognized that we had a square root of a squared minus u squared, and so we knew that we could use this first rule here. By using that first rule here, really we used the triangle. And the triangle allowed us to figure out what our opposite, adjacent, and hypotenuse were. The opposite, adjacent, and hypotenuse allowed us to get things in terms of theta instead of in terms of x. And this helped us out because we were able to use a trig derivative. So we found what x was, we found what dx was, because those were the things that we wanted to replace. We replaced them. We simplified. We found a Pythagorean identity. We simplified to the point where we knew how to integrate, and then we integrated. After we integrated, we had to make sure that everything was in terms of x again. And so we took what our cotangent was from our triangle, and we replaced it so everything would be in terms of x. Okay, now it's time for you to try one on your own. So I'm going to give you a problem to do. Go ahead and try this out, and then if you have any questions, drop it in the comments. So I want you to find the integral of 3 over x times the square root of 4 minus x squared dx.